Yeah, so as already been introduced, I'm Adam. I'm from Imperial College London, and I'll tell you a bit about hidden conflicts in neural
You
networks.
might need to use the keys, I believe, on the keyboard is how you're doing it right well.
All right, yeah,
Yeah.
thank you. That works. Right, so I guess in this setting, I probably don't need to motivate the need to explain machine learning models too much, because hopefully, as coming from the sort of fairness and transparency community, you already appreciate that it's important that we understand the decisions of our machine learning models. But what's true about these models is that quite often they are faced with conflicting information. So if you have a look at the example on the slide, let's say we have a very simple neural network that's trying to make classifications of how likely is someone to be suffering from a heart attack. And let's say for simplicity, we are only using two sets of features. One is whether they are experiencing chest pain, which of course increases the likelihood they might be suffering from a heart attack. If someone is having chest pain, maybe they might be having a heart attack. And the second feature is maybe the patient is also reporting that their symptoms are actually worsening with breathing, which on the other hand lowers the chance that this is being caused by a heart attack. So if you combine these together, maybe the model predicts that the likelihood that they actually have a heart attack is relatively low. But what's unfortunate is many feature attribution methods, so basically methods that try to gauge how important different features are to the prediction of the model, are actually not very good at attributing importance to these kind of conflicting features. So if you look at gradient-based explanations, you find that basically both of these features get an importance of 0, which is kind of misleading given that they are just canceling each other out. So that's the issue that we try to tackle in this research. First, we try to develop a sort of rigorous theory of conflict so that we can describe what they are and talk about them in a principled way. Then we introduce a new feature attribution method, which is aimed at actually being able to surface these conflicts and correctly attribute their importance. And finally, we explore some potential connections between conflicts and different kinds of distributional shifts. So that's basically situations where your data distribution suddenly changes, and whether there's anything we can find out about these kind of shifts when you look at the conflicts. So first I'll start with what is actually a conflict. So returning to the example that I showed, we can now try to drill a bit deeper and see whether we can try to formulate some kind of properties associated with conflicts. And first we can have a look at whether we can identify sets of features or pairs of features which counteract each other. So first, it is pretty clear that x2 in this case is counteracting x1, and the reason for that is if we remove x2, which is the feature that the problems of the patient worsen with breathing, then the output of the model actually changes to 0.9, so predicting a high risk of heart attack. So we can say that x2 is actually counteracting x1. The vice versa doesn't really hold, because if we remove the fact that the patient is experiencing chest pain and some of their other symptoms are worsening breathing, we still conclude there is very low risk of heart attack. So the vice versa doesn't actually hold. But even though there is only like one direction in which these features counteract each other, we can still say that the two pairs of features are actually in conflict, because we see being in conflict as a sort of symmetrical property. And I mean, this is just an example. You can find all the definitions in the paper. I didn't put them in the slides because we wouldn't be able to cover them in the sort of short time we have. Next, we can also ask whether the conflict is actually hidden, which means that whether it is able to be shown by certain kinds of feature attribution methods. And as I said, typical gradient-based methods don't show this kind of conflict, so that's why we treat it as sort of hidden, and that's where the name hidden conflicts comes from. And finally, we can also try to estimate the magnitude of the conflict, which is basically a measure of how much the output of the network can change if we do some interventions on the features involved in this conflict. And in this case, this conflict magnitude is 0.9, which means that the most we can sort of alter the output of our neural network by intervening on features in this conflict is 0.9. Now that we covered this ground of what actually are conflicts, we can also consider a natural question of how often these conflicts actually are, to see whether this is more of a theoretical problem or actual issue that happens with real models. And what we found across our experiments with several different data sets is that these conflicts are actually quite common. So what we found that on average about 49% of neurons in standard multilayer perceptrons are engaged in hidden conflicts. So the share of all conflicts are actually likely much greater than that. And in FT transformers, which is a specific kind of transformer architecture for tabular data, we found there is also a pretty decent share of conflicts, around 30% of hidden conflicts overall. So now that we can talk about conflicts, how can we actually surface them with explanation methods and feature attribution methods in particular? And what we do for this is that we develop a new feature attribution methods called CAFE, or conflict-aware feature-wise attributions. Sorry, that should be explanations. Which surfaces conflicts by separately considering both the positive and negative features at each layer of the network, and by sort of reasoning about how much these separate positive and negative features could affect the output if they were on their own. And this, as you can see, allows us to actually give weight to the input features even if they are engaged in this sort of conflict and cancel each other out. And what we actually show that is that CAFE is actually guaranteed to be what we call locally conflict-aware, so it's guaranteed to locally surface conflicts if it's applied to multi-layer perceptrons with ReLU activation functions when using CAFE under some specific settings, which isn't too difficult to achieve in practice. Now, of course, we also evaluated CAFE in terms of standard benchmarks and metrics for explanation methods. In particular, we were most looking at a property called faithfulness, which we measure through the inverse notion and infidelity. And what this is measuring is basically how well is an explanation method able to predict changes in the model output as we make some small perturbations to the model inputs. And what we found is that CAFE is actually very competitive with other alternative feature attribution methods in general. Quite often it's the best performing method, and also it is sometimes able to outperform approaches which take much more time to run, such as Shapley value sampling. And finally, we also looked at how might be conflicts related to correlation shifts and different kinds of distributional shifts in general. So what you can see in this figure is the distribution of what we call a conflict score, so basically a score which tries to quantify the degree to which there are conflicts. So if conflict source is higher, then there are more conflicts. Conflict score is lower, then there are less conflicts. And what we can see is that the orange sort of distribution, which is showing samples coming from a distribution with correlation shifts, so basically two variables which were correlated in the original training distribution now have different relationship. Then you can see that in this case we observe a higher share of conflicts as expected, because now the model is getting more conflict information from these shifted variables. The in-distribution data has sort of moderate share of conflicts. That's the sort of gray samples in the distribution. And finally, if we remove one of the features, which is another kind of potential shift, then the amount of conflicts decreases because there's one less feature to show conflict. So we think this could actually be a useful diagnostic tool for these kind of distributional shifts. So I'll just leave you with a few key takeaways. First, convex neural networks are a relatively common phenomenon, are often underreported by existing explanation methods and feature attribution methods in particular. We develop a new feature attribution methods, which is aiming to sort of mitigate this issue and has theoretical guarantees as well as sort of strong overall performance. And finally, correlation shifts may be associated with more pronounced conflicts, and this is potentially promising direction for future work. So with that, I would like to thank you very much for your attention and happy to take any questions.